So in the second part of this lesson, we're going to introduce a new formula. It's a little more complex than the ones we've done. You do not have to memorize it. On every single question, it will always be given to you, and you just have to figure out how to use it. So this is Newton's law of cooling. I'm going to read the question first, and then we'll start to talk about the formula. So this says a crime scene investigator is told by a detective working on a case that they believe a person was murdered 10 hours ago. The temperature of the room where the body was found was measured to be 68 degrees Fahrenheit. It is assumed that the temperature of the body when the person died was 98.6. The decay constant K for the temperature decrease for a dead human body is 0.1335 per hour. So that's talking about, it's a little more complicated than this, but like what percent the temperature of the body goes down relative to the room temperature around it. If it is true that a person died 10 hours ago, what should the temperature of the body be now to the nearest tenth of a degree? So if someone dies, I don't know, like murder scene, it says, and we're trying to figure out how long ago they died, this formula is basically what's used. It's a scientific formula, and it actually works for all different sorts of substances. As we'll see, it's just this decay constant is different depending on what substance we're talking about. So I'm going to try to scroll down just a little bit so I have room to write, but also see the formula. So looking at these variables, we're going to match them up. So T is the time in the given unit. That's the first thing I come to here. So this is 10, and right now we're measuring in hours. Okay. The temperature of the room where the body was found was 68 degrees Fahrenheit. So that's the temperature surrounding the object. So this is 68. Now this is T sub alpha is what we would say. Alpha stands for like the ambient temperature or the temperature of the surroundings. T sub 0 is the initial temperature of the object. So the initial temperature of the person is 98.6. And then it said we are finding the T by itself. I know this is confusing because there's multiple T's going on, and that is that one. So the decay constant is the last thing we have, and for a human body, that's 0.1335 per hour, which matches with our variables. We don't have to do any sort of crazy converting. So let's plug these numbers in. So I'm using this formula once again right here. So I'm finding T. My T sub alpha is 68. My T sub 0, or the starting temperature, is 98.6. We have another T sub alpha, which is 68. Then we just have the number E to the negative K. And then my little t, as I said, just to make it a little more confusing, we also have a little t, and we have all our big T's with our subscripts, is that. Now, in your calculator, because there are all numbers here, remember E is just a number, I can type this whole thing in exactly as it is. So especially if you have a graphing calculator or something online similar, it's helpful because you can make sure it looks right. So if I type that whole thing in, that would give me 76.1 degrees Celsius. Okay. Nope. I don't know where the Celsius came from. Fahrenheit. For some reason, I wrote Celsius on my page, but that doesn't make sense. That is not a reasonable temperature for a human body. Okay. So that's how the formula works. Now we're going to look at some problems that involve solving with this formula. So here's another one. Unfortunately, we're not going to be able to see the whole problem at the same time, so I'm going to kind of put information down here and scroll down. So this one has to do with hot water, okay, which also sits in a room and cools down. It says after heating up in a teapot, a cup of hot water is poured at a temperature of 201 degrees Fahrenheit. The cup sits to cool in a room at a temperature of 67 degrees Fahrenheit. Newton's law of cooling explains that the temperature of the cup of water will decrease proportionally to the difference between the temperature of the water and the temperature of the room, as given by the formula below. So here is our same formula. I'm going to transfer that information. So the initial temperature, starting temperature, is 201. And the temperature of the room surrounding the object is 67. So more of our information is going to come down the page a little bit. Here, the cup of water reaches the temperature of 190 Fahrenheit after 3 minutes. So we are told here, it already says minutes. So it's telling me in this problem, it's a little more specific. That's a 3, right? And then the 190, the temperature of the object after T minutes, it's telling me this now. And it's asking me to find the value of K to the nearest thousandth, okay? So this is my decay constant, and this is what I'm gonna put an X in for. That's what I'm trying to find. So we're gonna set up our equation with that information. There is a second question. I'm only answering this one first. Okay, so I'm stopping here. I'm answering this part of the question. So we're entering only the final temperature into the input box. So let's plug in these numbers into our formula. It does get a little tricky. I'm actually going to zoom so we can see the whole problem. Okay, so now we can see our formula too, and we have room to do the problem. So plugging in, I have 190 for the T by itself. I have 67 here. And we're looking for K, but we know T is 3, so I'm going to write -3. I could write the K. No, I'm just going to use a K here. I'm not going to use an X. Now, this looks at first glance like, well, why do we have these two 67s here? Can't they just cancel? Okay. Now, the issue becomes is that this parentheses is connected to the E. So we have to take things away piece by piece. So one thing we can do to start to make this simpler is I can simplify this, right? Because that's in parentheses, so that's fine. So I'm going to make this a little easier. That's 134 e to the -3k. Just a side note, I'm going to have to erase part of the problem at some point because I am like kind of zoomed weird and I'm in a certain computer, but leave space because we have other stuff. So you guys should have plenty of room. So the first thing I need to do, sorry, this didn't get copied down. That's 67 correctly from the problem up top. So we need to subtract 67 here. Okay. And that's going to give me 123 equals 134 e to the -3k. So now this should look super familiar. We have multiplication. We're trying to get into Venn form. So I divide by 134. I'm going to be keeping the whole decimal in my calculator. So I'm going to come over here actually to give myself a little more room. This problem here ends up equaling 0.918. That's rounded, but we're keeping the whole thing going. Okay. Now we're in Venn form, so we're ready for logarithmic form. So I'm going to write this with ln. This is log base e I recognize. So this is ln of my number, which is 0.918. Remember, the e is hiding here, but we don't have to write it. Equals the exponent, which is -3k. So from here, I could type this in. I'm just going to divide by -3. Type this whole thing in. Once again, typing in that whole decimal or highlighting it. And my value of k to the nearest thousandth, which is 3 decimal places, is 0.29. Now, a little differently than what we've talked about before, this problem tells me to round that number to the nearest thousandth. So that's fine. I can round that to the nearest thousandth, and I'm going to just use the 0.029 because I was directed to in the problem. So to do the next part, it says use the resulting equation to determine the Fahrenheit temperature of the cup of water to the nearest degree after 5 minutes. Now, room-wise, I'm going to have to erase. You guys should be able to write this below. All of this information I just did is working towards finding the value of k, so that's the part that I'm going to keep here. And then do the second part of the problem. So looking at this, now that I know k, my other new information I have is that this is now 5, and I now know this is 0.029. And that's what I'm looking for, the temperature after 5 minutes. So some of my variables have stayed the same, some have changed. So plugging them in, this part is still the same. And we have E, and my K is 0.029 times 5. So if I now I can type in my calculator because we have all numbers. So the resulting temperature after 5 minutes is 183 degrees. So we have one more problem here that we're going to do, and I'm going to work through this one a little more quickly. So this one has to do with a turkey that's put in the oven. So this is called Newton's law of cooling, but it's also Newton's law of heating. And you'll see the way things kind of work out, and I'll talk about that a little bit, is that it works in both directions. So if I take a cold turkey and I put a hot oven, it's also increasing towards the oven's temperature exponentially. So reading through the problem, the turkey is placed in the oven. So this 70 is its initial temperature when it's placed in the oven. T sub alpha, the temperature of the surroundings, is 305. That's the oven temperature. The time and hours we don't know. It says down here, basically this is just more telling us how Newton's law of cooling works. Down here it says the turkey reaches a temperature of 100 after 1.5 hours, and we're once again finding the value of K. So here we know it's going to be 100. This says hours, so we're good to go. And we're trying to find K. So we're going to set up that equation very similarly to the last one. As I said, I'll do this one a little quicker. So let me just flip my page. So we have 100 T equals 305 plus 70 minus 305. So this ends up being negative, which kind of flips things. So even though we're cooling or even though we're heating up, it ends up working out. So it has to do with this negative number being multiplied by the exponential. It kind of flips things back to positive and makes that function increase if you were interested about that. So this is negative 1.5K here. So steps, we can simplify this, but I'm also going to subtract this at the same time. So we get negative 205 equals, this simplifies to negative 235 e to the negative 1.5k. We are going to divide by negative 235 to get it to Venn form. So this is going to give me 0.872 equals e to the negative 1.5k. We're going to put it in log form. So because this is base e, we can call this ln of the number equals negative 1.5k. And then we're going to divide by negative 1.5, keeping this whole decimal on our calculator. And that's going to give me a k value rounded to the nearest thousandth of 0.091. The problem tells me to round to the nearest thousandth, so I do not need to use this whole decimal again. So I'm going to erase the problem to this point, and we'll use that value of k to ultimately figure out the temperature of the turkey to the nearest degree after 4.5 hours. Okay, so I'm going to erase this section now. And we are now looking for 4.5 hours. We don't know this, but we did solve and find that K is 0.091. So the temperature and I'm not going to talk through this, we're just writing down the formula, right? So this is KT and if I typed that whole thing in my calculator, that would give me 149 degrees.